So let's take a look at this piecewise function defined over here that we have graphed. And we see that we've got some places in the function where the function is not defined. Actually, just one place right here at -2. The function's not defined. It is defined everywhere else. So the domain is all real numbers except at -2. And we've got some weirdness happening with some holes in here and just a point hanging out by itself. So we're going to talk about limits here. So this is the official definition of a limit. There's actually a little more precise definition, but this is a definition of a limit that we're going to start with. They're calling it a preliminary definition. Suppose a function f is defined for all x near a, except possibly at a. So a is some x value. If f of x is arbitrarily close to L, some y value, some output, as close as we like, for all x sufficiently close but not equal to a, we write the limit as x approaches a of f of x equals L. Okay, and this is how we say it. The limit of f of x as x approaches a. Sometimes I switch these around. I kind of like to say the limit as x approaches a of f of x, and that's fine as well. So to get a picture of what's happening here, let's say we've got some function and we've got some input value a, and we want to know as x approaches a, that's what these arrows are signifying down here. As x approaches a, what is f of x approaching? And we really do need to look at it from both sides. Now we're going to talk about in a minute just looking at it from one side. But we want to look at x values bigger than a that are getting close to a and x values less than a that are getting close to a, and look at those outputs. So in this case, these outputs are approaching some y value from both sides. And that y value then would be the limit. So in this case, this f of a is the limit. Now, sometimes f of a is not necessarily the limit. Let's say f of a is meaning where the function's defined at a. So let's say this is not the value of f of a. Let's cross this out. Let's say there's a hole here. Okay, and the actual value of f of a is up here. So this is the value of the function at a. But the function itself, as x gets close to a, is approaching this y value. Let's call this y value L. Okay, so the limit as x approaches a of f of x is L. So the limit as x approaches a of f of x doesn't necessarily have to equal f of a. It might, but it doesn't have to, okay? It doesn't have to. It's really about what is f of x approaching as x approaches a. All right, so to practice that a little bit, we're going to go through these problems here based on this graph. So if you haven't done that, take a second and pause the video and go answer all those questions, and then we'll go through them. So the first question asks us, what is f of 3? So this isn't a limit. It's literally, what is the value of the function at 3? So we can just go down here and evaluate that. 3 is bigger than 2, so 3 minus 5 is -2. And you could look on the graph to see that as well at the point 3, -2 right here. So what is the limit as x approaches 3 of f of x? What is the limit as x approaches 3? Well, here's 3 right here, and it looks like the y values are approaching -2 as well. All right, so nothing too complicated happening there. Let's see, what is f of -3? Well, f of -3 is going to be at this part of the function, so 1/2 times -3 squared would be positive 4.5. What's the limit as x approaches -3? Well, that's also 4.5. Okay, there's nothing weird happening here. It's just a smooth curve. So when you have a nice smooth curve like this, the value of the function is going to equal the limit. All right, let's check out f of 0. F of 0 looks to be -1. What's the limit as x approaches 0 of f of x? What are the y values approaching as x gets close to 0? Well, they're approaching -1. All right, what is f of -2? Now we're going to get kind of interesting here. What is f of -2? Well, there is no value here, right? So it's undefined. It's undefined. What is the limit as x approaches -2? Well, if I look at how approaching from the left, it looks like the y value is approaching +2. If I look at approaching x from the right, it looks like the y value is approaching 1. Well, that's kind of weird. So, I don't know. Is it 2? Is it 1? It kind of looks like it's different from both sides. We're going to leave that there and come back to this one in a little bit. All right, so the next one says, what is f of 2? Well, the value of the function at 2 is -1. That's this point right here. What is the limit as x approaches 2? So if we look at as x is approaching 2 from the left, the y value is getting close to -3. If I look at approaching 2 from the right, this way, from approaching 2 from the right, the y value is getting close to -3 as well. So the limit as x approaches 2 is -3. So this is really our first example right here of where the value of the function is not necessarily equal to the limit. And we can see that in the graph when we have a hole and then a jump, where we have the value of the function is not equal to where it looks like the function is going to end up being defined. All right, so let's go back and talk about this business right here. What's happening here at -2? Well, we have a definition of a one-sided limit. So we have a right-sided limit and a left-sided limit. Why don't you pause the video for a minute and read through these definitions. All right, so the big distinction here is we're only looking at x values bigger than a. All right, we're only looking at x values bigger than a when we're doing the right-hand limit, right side limit. And it's denoted like this with a little a with a plus sign. Okay, similarly, if we want to look at a left-hand limit, we're only going to look at x's less than a, and then we're going to denote that with a with a little minus sign. So let's go back to this -2 problem here, because we saw two different limits, right? So if I look at this direction here, if I'm looking here, I'm looking at x values that are less than -2. So in that case, I could say the limit as x approaches -2 from the left, that's the little negative thing, from the left, the y value is approaching 2. Then I could say, let's look at it from the right. So now I'm going to look at x values that are bigger than -2. So I could say the limit as x approaches -2 from the right, denoted with a little plus sign, well, that's equal to +1. All right? So why don't you take a minute and go to activity 3 and try these problems. There's actually a typo here. These E and F are exactly the same. So this should be a minus. So blot that out and make it a negative sign. So -2 from the left and -2 from the right. All right, pause the video and run through those. All right, so we have some similar questions, but now we're breaking it down from the left and the right. So we did f of 0 before, and the value at 0 is -1, right here. So here I want the limit as x approaches 0 from the right. So I'm looking at it this direction. I want to approach 0 from the right. And it looks like the y value is approaching -1. And here I'm looking approaching from the left, and the y value is also -1. So this is all nice, right? No weirdness. And this is what's going to happen with limits when you have a nice connected, what we're going to call continuous function here. You're going to have your left-hand limit, your right-hand limit, and your value of your function all be the same thing. That's when life is easy. Now let's look at x is -2. Now it's a little weirder, right? Around this x equals -2 point. So the value at -2, remember that was undefined. And we talked about this a second ago in the limit when we did this, this problem up here. We said, hey, as x approaches -2 from the right, let's use blue. From the right, this way, the y value is getting closer and closer and closer to 1. As x approaches -2 from the left, the y value is getting closer and closer and closer to +2. All right, let's look at f of 2. So f of 2, right here we have some weirdness when x is 2. The value of the function is -1. As x approaches 2 from the right, this way, the value of the function is headed towards -3. As x approaches -2 from the left, the value of the function is headed towards -3. So here we have the left-hand limit and the right-hand limit equal to each other, but that's not the value of the function. All right, so this left-hand limit and right-hand limit are used to define what it means to have a limit at any point. So let's read through this. Assume f is defined for all x near a, except possibly at a. It doesn't have to be defined at a, like this, like at -2, okay? But it's defined near -2. Then the limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the right equals L and the limit as x approaches a from the left equals L. Okay, so in order for the limit as x approaches a to be defined, it has to approach the same value, L, from the right and from the left. Okay, if it doesn't approach L from the right and from the left, then we say that this limit right here does not exist. All right, let's write that out. If the limit as x approaches a from the right does not equal the limit as x approaches a from the left, then the limit as x approaches a of f of x does not exist. We say does not exist. Can you find a place on this graph where the limit does not exist? For what value of x on this graph does the limit not exist? All right, in other words, for what value of x does the limit from the left not equal the limit from the right? Well, hopefully you're saying -2, right? So the limit as x approaches -2 from the right is 1. And the limit as x approaches -2 from the left is 2. And those are not the same value. So the limit as x approaches -2 of f of x without any distinction from the left or the right does not exist. So that takes us back to activity 1, where we were asked this question: what is the limit as x approaches -2 of f of x? And we said, well, it looks like it's 2 from one side and 1 from the other side, and that is true, and those are the left and right hand limits, but because they are different, the answer to question H is does not exist. Alrighty. So the last little activity we're going to do here is to evaluate some tougher limits by using Desmos to help us out. So I'm going to get you guys started on A, B, and C, and then have you mess around with D, E, and F. So the first thing we want to do is go to Desmos and graph this function, x minus 9 over square root x minus 3. So we're going to go y equals parentheses x minus 9 over, and you can use SQ square root of x, and you got to move your cursor out from under your, oh, it was 3, wasn't it? Out from under your square root. Okay, so there's our function, and we can move it around and look at it here. All right, let's go see, what are we supposed to, we're supposed to be doing the limit as x approaches 9 from the left. Oh, sorry about that. The limit as x approaches 9 from the right, and the limit as x approaches 9. So we need to see what's happening around 9. And you can zoom in. Let's see. So 9 is right here. So what you could do is take your cursor and move it along here, and you see the values of the point. Now right at 9, what's going to happen? All right, what's going to happen when we plug in 9? Oh, did I get it? There we go. If I plug in 9, it's undefined. If I put 9 in my denominator, I get 3 minus 3 is 0. I get 0 over 0. So the actual value of the function at 9 does not exist. But what does it look like the y values are getting close to? It's 5.8, 5.8, 5.9, 5.93, 5.94. Oh, now it's 6. It's 6. Looks like it's approaching 6 from the right and 6 from the left, even though it's undefined right there. Okay, so based on what I see on that graph, it looks like from the left it's approaching 6, from the right it's approaching 6, so the actual limit is 6 because these two things are equal to each other. Now I didn't ask you this, but the value of the function at 9 of this function right here is undefined. Undefined. Okay, so I want you guys to do the same thing for D, E, and F. Graph that, take a look, and see what you see. And have a great day.